क्या करना है? Okay, so welcome back. We are going to start the lecture 3 for day 1, which will be mostly the modeling, characteristics and application of fuel cell. So mostly the theory part you understood, and fuel cell chemicals and all those involved chemical reactions. And now mostly the modeling aspect we'll be discussing in this third lecture. Over to you, Professor.
Hello. Okay, all good. Okay, welcome back. So, this section we may mostly talk about the modeling, because we already talk about the applications. I am not going to repeat it, but we mostly talk about fuel cell modeling. Now, when you talk about the modeling, that means that we are talking about the mathematics and simulation based representation of fuel cell behavior. Like, if you remember that we shown like IV curves, the relation between voltage and current, and also it could be relation between voltage, power and so on. So, if we want to exactly replicate that behavior, we need to develop the model, because at then as an engineer we always look for the differential algebraic equation, and using that we do all sort of studies. And you want to do anything like the system design, control, optimization, system integration, or even like integrating in the vehicle. So, the first requirement that you have to have accurate modeling. Unless you have got accurate modeling, whatever control, design, optimization you are going to do, and if you implement in the real system, you are not going to get your desired performance. So, that is why modeling is quite important. And again, model actually involves different level of details, like the electrode, electrolyte, either it is a single cell or stack, or even the system level. And why it is important to do the modeling? Because if you want to predict like whatever voltage, current, power you are going to get from the system, you need to do the modeling. And also if you want to analyze the efficiency, so we did mention like that 40%, 60%, 50% efficiency, but that is the standard one. But when you are going to design something and use for particular application, you might not get your desired efficiency, right? And if you want to determine by yourself, you have to have the modeling, and then you can analyze efficiency. You can analyze what sort of fuel consumption be like for a particular fuel cell for a particular application. So, to understand the level of fuel cell that you need for a particular application. So, let us say you for example have 5 kilowatt electrolyzer in a lab or in your building, and you want to know like what sort of fuel I need for using for a particular period of time or to supply load for a particular application. So, that is why you need the modeling. And if you want to design control, the first thing as you know that we need to know the modeling. If you want to optimize the thermal, water and fuel management, also you need the modeling. And later if you want to facilitate the system integration with power electronics, inverter, converter, even like if you want to add additional battery, that also we need to do the modeling first and see like the system response, and then we can like in the either real application or laboratory environment, we can make the real system. And definitely the modeling enable like real time simulation using the hardware loop as well. So, that is also to do that also you need the modeling. Now, there are for fuel cell in the literature mostly 4 different types of model available, and the first one we call it empirical models. So, the empirical model mainly based on your experimental lab experimental studies. So, you do experiment, you measure some variables or some parameters, and then using that one you use curve fitting method to exactly analyze the system behavior. But here we do not depend on the system either physical or circuit model. We just measure some parameter and using that one by trial and error method we develop the curve fitting, using curve fitting the model, and then we using that model. So, mainly when I say the model, mainly this one like the voltage current relationship from your test data, but we do not use like any physical model or electrical equivalent circuit model. Just from like experiment you can get that empirical simple model, and whatever like model that data that you collect, and using the curve fitting method, at then you are going to get a equation something like that, which again represent the typical typical like the voltage equation. Now the next one, so the next one is like semi empirical. So, semi empirical means that you are combining empirical, but at the same time you are also considering like that some physical characteristic of the system, and that physical characteristics actually normally like if it is a cell level, then we use like this equation, but we can also use the stack level equation as well. Now, what we do, we normally start with here this characteristic equation, and then after that we use the empirical like your data from experiment just to better tune the system to get exact like system behavior. And this equation again, if you can remember that we talked about that IV curve, where in the IV curve we have got 3 regions like activation, ohmic and concentration, and these 3 nothing but the losses, right. So, whatever internally voltage you getting from the cell, and if you subtract these 3 losses, you are going to get the cell output voltage. Now, the third one we call it like physics based or detailed like the dynamic model. So, this one actually consider not only like the electrochemical that I mentioned previously. So, this one just like the electrochemical, but it does consider like thermal and also fluid, anode, cathode, all the dynamics. So if you remember, there is some reaction happening in the anode, some reaction happening in the cathode, and also like heat flow, water flow. So if we combine all this dynamics, then we're gonna get that detailed physics based full dynamic model, and it capture the transient behavior, the temperature gradient, water transport, fuel, air flows, everything. But the other model that I mentioned previously, it doesn't include temperature changes. It just consider constant temperature, and then constant water flow, constant air flow. So it doesn't consider any changes, all those parameters. But it does require like significant computational resources, because you are considering so many nonlinear model that require computational power to solve it. But it definitely better and more accurate than other method. If you want to do like detailed system level design, system level optimization, and further academic research. Also it depends like what type of research. Some research might be enough just considering the simple equivalent circuit as well. And the final one, what we do, we like develop the equivalent circuit of the fuel cell, and then from that we develop the using like KVL, KCL, like Kirchhoff voltage law, current law. From that actually we develop the model. And this is like all the parameters that actually you need if you want to do fuel cell modeling. So you need the cell voltage, current, temperature, fuel and oxidant flow rates, like humidity level, pressure effect, internal resistance, losses, hydrogen and air utilization rates, heat and water management. So this one actually for the detailed model that I mentioned. But what happened in many cases, it's not easy to get all the data you need for a particular system. So that's why in many cases, that's why we like we had to consider constant and neglect many parameters. But as I mentioned, like depending on the application, sometime simple model will be more than enough, because it's going to reduce your computational power as well as computational complexity as well. And normally like in terms of software, MATLAB Simulink, for control design, system simulation, real-time testing, you can use that. But if you want to like having like physics level characteristics, then you need to go like the COMSOL for having like chemical, thermal, and if you want to do fluid models, then I think this one would be the best software. And CFD based modeling for flow and heat transfer, probably ANSYS would be the better choice. Like for optimization, if you don't want to write codes, then like Homer might be an option that you can utilize for just doing the system level optimization, where you do have fuel cell, but you have other DG and other devices as well. And if you want to do like network level simulation, either mechanical or even like electromagnetic. So for electromagnetic, probably PSCAD is the best option. PSSE you can use for electromechanical, where it doesn't involve the dynamics from power power electronics. But if you want to capture the power electronics, then I think PSCAD is the best solution. So again, depending on your research, which one more important for you, based on that you can identify which software either you or your student gonna be utilizing. And again, we already mentioned all of them, like the application. Now the first one, I'm now going more detail about these four methods. So, the first one, I mean, as I said that it does not capture the detailed electromechanical, chemical or physical process that is happening inside the fuel cell. Instead of that, what we just do, we do some testing, we measure like voltage, current, and then whatever unknown parameter. So, let us say, I mean, this is like the characteristic curve. So, you might measure like output voltage, resistance, but not like all the like variable is known here. So, there you can see there are some coefficient, which is one of them related with the resistive losses, which is definitely the related with the current, and the other one the relation is like logarithm. So, if you can remember in the initial that was like exponential logarithm relation. So, you need to have some logarithmic term in your characteristics equation, and here we have got one definitely that is relevant with the current, but other one like is small constant, because sometime if you have got 0 here, you might have like singularity problem. So, that is why we just use a small constant to avoid like that singularity problem here. So, what we will do that by knowing like whatever you know here, but this K1, K2, K3 maybe you can assume, but K1, K2 by curve fitting method with the measured value and then unknown whatever parameter you have, you assume, and then you do have characteristic curve. So, by playing with that, at the end you have to make sure that the characteristic curve actually it matches with the originally characteristic curve of the fuel cell. So, that is how you are going to do the empirical model. Although I mean it's quite simple, it's easy to implement in simulation like MATLAB Simulink. If you don't want to use the existing one, and if you want to develop it just like a simple equation, and you can easily I mean implement it any software. And as it's simple, you're going to have like fast computation, and sometimes if you want to do real time, then you have to do like very quick calculation, right? So, if you have got like let us say you need 10 minutes, then there will be like a long delay. You might not be able to have real time control or even like hardware in loop simulation. In that case, I mean this model might be okay, and also might be okay for like an initial level system design initially, and then later you can finalize and optimize using like a very detailed model, because when you're going to do like feasibility, you don't need exact I mean very detailed model. Feasibility is something like that, it might be possible and it makes sense, and then later I mean you can have very detailed model. But definitely I mean it has got number of limitation, because when you do experiment, we do consider certain operating condition, right. So, let us say you are considering one particular fuel cell, it has got particular voltage, current and power rating, and also particular temperature that you are doing. But if something changes, that you are changing the fuel cell rating, right, or also you are changing the input hydrogen flow. So, anything changes, you have to do the experiment again. So, only that model is valid only for the condition that you have I mean did the experiment. And as I mentioned that it does not capture temperature variation, gas composition changes or any transient state of behavior. And as I said that you need new experiment to update the model if anything changes. So, that is the disadvantage, but good thing is that it is very simple. It does have some application, as I mentioned, that preliminary design, real time simulation, energy management, but not the control. Energy management might be okay, but control algorithm for I mean the validation I mean is proper, but for the initial maybe you have to consider the detailed model. And rapid performance estimation like in vehicle and stationary system level simulation. So, if you want to estimate something rapidly, I mean this model might be okay. And the next one is semi-empirical. So, semi-empirical means that it does consider electrochemical. The previous one, even it does not consider electrochemical. So, it considered that empirical plus that electrochemical model, and this is the equation like for electrochemical model, where again I mean it does have these three losses, and this is that reversible voltage based on that thermodynamics, and these three losses we already talked about. So, what we did, we used this model, and then later I mean we use that test result to see that whatever we are getting here are we getting from the test measurement, and then we need to make some changes from the model and from the experiment to exactly I mean mimic the behavior of the fuel cell. So, it is just the combination of these two. So, that in the previous equation you see that the first that reversible voltage, you can actually model that electrochemical model that I mentioned. So, this is the electrochemical model that we are just combining with that voltage equation. Now, for all these parameters there are some like given parameters, but again I mean this might vary from like one fuel cell to another fuel cell, but this is some of the parameter, standard parameter like for E0 in most of the cases like in 1.2 to 1.3, if your temperature like around 25 degree, but if changes then definitely there is going to change. So, you also know this R, which is like the universal gas constant, T, I mean that is a temperature in Kelvin, but you need, if you know like degree centigrade, then you need to convert into Kelvin by adding 273, and F, that Faraday's constant, that is also known, and this is some of the pressure value of hydrogen, oxygen and water. So, using all of this and activation equation that I already mentioned in the previous cases. So, using this, and you can calculate ohmic, concentration, all of these three like losses using this three equation, and then this is again like the constant. So, this constant sometime from your experience or even like through that experimental process you can calculate, and then you can do your model. So, again if you compare with the previous one, the key difference, the empirical is just like experiment. This is like theoretical principle plus experiment is derived from like the curve fitting, but this is more like physical laws with just some adjusting the parameter, and it's slightly bit more complex than that one, although it's not complex as the detailed mathematical model, slightly more computational burden slightly higher for this one compared to that one, but definitely that one accuracy will be higher than this one. So, this is like some of the application. If you want to do the performance analysis of different, you can use this method. Control system for fuel cell powertrain, sometime for microgrid also you can do that. In cases like you consider that the temperature and other parameter will not change significantly, then probably it's okay to use this model. Power electronics design, simulation of hybrid system like the battery fuel cell, sensitivity analysis, that like the model for particular one temperature, then if you change the temperature, humidity, how your system is behaving, probably you can do that. Again it has some application advantage, mainly in terms of accuracy, but definitely there are some again like limitation as well. So, it still needs some experimental data, may not be exactly capturing the dynamic behavior like dynamic state shutdown, and also it might be simplified compared to CFD 3D multiphysics model, and accuracy depend on the quality and range of the fitted data as well. So, the experimental data and others also actually heavily contribute in the accuracy of the modeling. And then this is like the most detailed dynamic model, which is physics based model that actually captures the internal electrochemical that we mentioned, but on top of electrochemical, the thermal, fluid, electrical process in the system using the fundamental in the physical law. And this model given like very detailed insight into transient behavior, which is good for if you want to design like define robust control, and also you want to do the performance level optimization as well. Again, this comparison I'm going to skip it. Only thing is that it will be more like complexity higher, computational cost higher, but its accuracy will be better than other two. For physics based dynamics model, you are considering electrochemical reaction that's happening in anode, cathode, that's also including charge transfer, mass transport. So, all of this included here. So, when I say like the charge transport, that's actually nothing but the movement of electron and ion. So, if you remember that in the previous class we did mention that where proton, electron, they are actually passing from either anode to cathode or vice versa. So, that's charge transport or that's ionic and electronic conductivity happening within electrolyte and electrolytes, that actually included in this model. And also the mass transport, that's considered the transport of reactants like hydrogen, oxygen, and also product like water within the fuel cell, including like diffusion, convection, all of them actually consider. And we also do consider heat transfer mechanism like conduction, convection, radiation, and that's actually happen in the real system. So, that also include in this model. And all the losses like the voltage losses that we mentioned already, that's 3 losses that do consider to predict accurate cell voltage, and the temperature, pressure, reactance flow, all are considered, all operating condition considered here. And also it does model the transient behavior of the fuel cell, like if you have like load changing, which is also good for understanding and controlling the fuel cell system. Now, in terms of mathematics, we already explained that electrochemical dynamics, the same equation, that's we consider the semi-empirical model, but on top of that we do consider the mass transport dynamics, which include like the gas flow rates, diffusion through gas, diffusion layer, and then reaction consumption at catalyst layer, and that's how actually we use that balancing equation using the charge in and out, the voltages, and here these are the parameters you need here, like the sorry, this one actually for this equation, but for here only common thing that you need to know the Faraday's constant, but charge in and out, that's actually need to model that. But this is again like the single dimension, but it can be also like in many cases people use like 2 dimension, 3 dimension as well. But in most cases single dimension is more than enough. And then you do consider charge transport dynamics, That's I mentioned like in previous cases that electrical and photonic conductivity. We also consider membrane potential and the current density. Using these two equations, you can use the charge dynamics, and then for thermal, again I mean for thermal you have got heat generation, heat losses, and then whatever in the heat actually loss and generation, and the difference, you know, I mean in if it is like steady state, then I mean it's gonna be 0. Otherwise, that difference actually give you that you know, the changes in the temperature, I mean temperature dynamics within that in a particular system. So it does involve like electrochemical reaction, home heating, and heat losses to the surrounding, and these are the parameter you need I mean to model that thermodynamics, like, you know, mass of the fuel cell stack, specific heat capacity, cell temperature, total heat generated, and total heat losses to the surrounding. And why actually thermal model is actually important, because if you like, you know, want to optimize that, you know, operating condition like temperature, flow rate, then I mean we need that thermal modeling. Even if you want to design control system that works like, you know, in defined work environment. So let's say you are having that fuel cell in the system where the weather is cold, and if somewhere you place the fuel cell which is like have hot weather, right? So if you want to make sure that it works for the different, like, you know, temperature, then I mean you need that model to consider in your control design system. But if you think that the control that you are designing, temperature will not change that significantly, then I mean it's okay to neglect that one. And also like the component sizing and selection for your cooling system, like, you know, radiator pump, and if you want to determine exactly there what size of pump, what size of radiator you need for a given fuel cell system, then I mean you need that, you know, thermal model. And if other thing, if you want to predict the degradation, because you know, like the battery, fuel cell, whatever you have, I mean with respect to time, its capacity will deteriorate. And yeah, if you want to predict, you know, what might be the, you know, outcome you get after 5 years, then also I mean you need to have this modeling included in your overall system. And even like the system level, you know, integration for larger like vehicle, stationary power plant, I mean thermal model will give the more accurate, you know, performance for your design controller. So that's thermal model, as already mentioned, like that that heat generation, it might happen through your electrochemical reaction, and also losses, heat transfer like conduction, that's already you know, might be within the stack and the cooling system. Individual component like the membrane, electrodes, bipolar cooling system are also needed to capture the thermal behavior. And depending on, again, like, you know, either steady state or more dynamic, you prefer, based on that, I mean you need to decide either you're gonna consider like constant temperature or like the variable temperature. And as I mentioned that it could be like, you know, one dimensional, two dimensional, or even third dimensional, depending on, like, you know, if you just consider variation like in a one direction, often like how the gas is following, then one dimensional might be okay. But if you consider the variation in two direction, then in most of the cases one, like, you know, perpendicular to the gas flow, then I mean you need the two dimensional. And three dimensional, if you consider temperature in all three dimension, then I mean you might need three dimensional model. And here some of the applications I already mentioned, like most of them, that you need to consider this type of model. And the final one, we also need like in water humidity management system. It does consider, I mean, these few things, which mostly, I mean, economical, I mean, important when you do that in a PM fuel cell. Now, again, I mean, as it has got differential equation, so that means it will have like your state variables. Now, if you consider the most simplest one, I mean, it has got 5 state variable, that means 5 differential equation, and this state variable that, you know, hydrogen concentration at anode, oxygen concentration, membrane hydration level, temperature, and cell voltage. And this typical 5 equation, that's going to give you this 5 state variable. But here again, I mean, we have number of things that we make assumption. But using that one, I mean, but if you say that you are not going to make any assumption, then it might be like, you know, 7th, or it might go 7th or 8th order model, which even would be like, you know, more complex. But in most of the cases, this simplified dynamic model where we have got 5, you know, differential equation, that's, you know, might be, you know, okay, I mean, to have your I mean, overall system model. Like again, I mean, this using state variable, using that hydrogen mass balance in the anode, where you do have like the flow rate, which is denoted by the Q, flow rate in, out, and then your anode compartment volume V, cell current, and Faraday's law. Using that one, you can actually model that hydrogen mass balance in the anode. And then next one, oxygen concentration. So that one, oxygen's balance equation, again, I mean, quite similar. You have like only, you know, oxygen in and out instead of the previous one, like hydrogen, because in the anode we have got hydrogen input, in the cathode we have got oxygen input. So only the difference, this is the cathode volume, and previous one it has got anode volume. But other than that, all other parameters quite similar. And then for membrane water content dynamics, that's given by this equation, where this one just like a, you know, constant coefficient, this is another constant, and this one equilibrium membrane water content. So using that lambda, like this is we consider constant, but this lambda is variable, that in water content dynamics. So we can use that equation, I mean, to model the water content dynamics. And then thermal dynamics, again, this is like the single dimensional model, where you consider the heat generation and heat losses, and you need the mass and heat capacity, and using that one, where T is the variable here, temperature. So that's how you can model the thermal dynamics. This one we already mentioned in the previous cases. The cell voltage, which is semi-empirical, we already discussed this model. So using that one, you have got the cell voltages. Now, to model that, finally you need these parameter, which you might get, you know, some of that when you buy the fuel cell, some of the parameter might be given in with the product that you buy, and in many cases if not, then I mean you might need to do some experiment or other way, I mean you have to make some assumption, then I mean you can have the overall model. And then, like, you know, as I mentioned, the control design, it could be like a simple PID, or even like if you want to go like, you know, very robust like model predictive control, or there are also many like, you know, other robust control technique as well. So if you want to go for those sort of control, I mean this model, you know, might be the best one. system level management model, and for educational purpose, this is also, I mean, you can use it to find out exact the system. Now, if you want to practice this, these are the some of the like typical values given, just for this modeling purpose. If you are interested, you just go like MATLAB or other software, use this parameter, and then you play with that one. And then the final one, so as you know that like as a electrical engineer, we always interested for equivalent circuit. Like if you think about like electrical machines or electrical generator, transmission line, even what we do, always we use like equivalent circuit. I mean for like doing analysis and different other studies as well. So this one, I mean, we try to relate using that voltage source, resistance, inductance, capacitance. Using that one also, I mean, we do have, I mean, the modeling. So you can again, I mean, here that either fuel cell or stack level. In the model, you will find 7, 8, or even more than different types of model. Even you can just get it for here, but again, I mean, in many cases people just use in many cases like one resistor here, capacitor, and one series resistor. That's actually in many cases quite enough actually to model the behavior of the fuel cell. And definitely, I mean, if you have got converter, inverter, you need to also model those part as well. But here I just included the fuel cell stack and the one like buck converter. We didn't consider the inverter. So using this one, I mean, just applying KVL, KCL, like for example here for the voltage, like that that reverse voltage and that the losses that we mentioned, these three things with the reverse. Actually, this is the same equation, but only just using V instead of E. So we can use that for like the voltage equation, but for like other cases, for example here, if you see like in the very like the right hand side, so if you consider this loop, right, we can easily apply KVL here. So how many voltage we have got? This voltage, and this voltage, right? 3 voltages. So using that KVL, you can easily relate these 3 voltages. So when you have got like inductance, so here we have got inductance capacitance because we did consider the DC to DC converter, and this is actually coming from DC to DC converter. So using capacitor, inductor, I believe you know how to calculate the voltage L di by dt, and from that you will get the this current. And once you know this current, if you consider this node, you can apply KCL where you have got 3 current, right? This IL, IC, and electrolyzer current. So if you relate these 3 current, you can easily then represent that IC using that capacitor voltage equation, and then is just by doing some simplification. That's for the right hand side. If you again then apply in the left hand side, I'll finish the KVL in the loop, then I mean you can get this equation. Now again, I mean if you apply KCL, you will get this 3 current. So what I'm saying that by just applying this KCL, KVL, this is very simple. I think every one of you know that. But after that, if you want to have like the state space model, I believe you already, all of you know, like this is the state vector, A vector which is related to state variable, and the B matrix related to input control. This is the measured output matrix. In most of the cases, I mean, you might get 0 here. So by doing that, I mean, finally, I've given like all the matrices here. So you can find all the metrics, and as you know that once you have this statistics model, it's very easy to do other study. For example, if you want to do the, let's say, eigenvalue analysis in MATLAB, if you just write EIG of matrix, this one is going to give you all the modes and eigenvalue. That's going to give you that whether the system is unstable or unstable. Even if you do number of like control doing the transfer function, if you want to do like different types of plotting from that one, if you want to tune your either PI or PID control, you can do actually many things once you have this mathematical model and the transfer function. So one of you already mentioned the previous time that how we do the maximum power point. So this is like your voltage, right? And this is current. So if you multiply like the voltage and current, you're gonna get the power. So here, this is maximum voltage but the minimum current, so you'll get minimum like the power. And then in different points, if you multiply voltage and current, your power curve will be like this, right? And then you're going to find at what point I'm going to get the maximum power. And then your MPPT control, again, I mean, for MPPT there are different algorithms that you can use to find out exactly the maximum power point. But in many cases what we do that we make some changes in the voltage and we see that whether power is either increasing or decreasing. For example, if it is here, if you make changes, it's going to increase. But after going for maximum, if it changes, it's going to be reducing. So that changes is either positive or negative. That's how you can find the maximum. But there are many ways, and recently people are using even like AI and very advanced level of control technique for MPPT control as well. And later, I mean, if you want to find out that characteristics by having the sensitivity analysis, for example, if you change the fuel level, how that IV curve is changing. So here you can see that like 100%, 80, 60, 40, how that characteristic curve going to be changing. And you see that for every curve, if you do MPPT, it's going to be actually different. Same for like if the current density changes, how it changes the voltage, different voltage. That also, I mean, you can do from that simple mathematical model. You can also do like if, for example, changing the temperature and pressure, how like that relation is changing. There will be some changes, but as I say, like in many cases, if that changes is not significant, then I mean you can make the temperature constant. But here you can see that if you change temperature, pressure, your voltage, current, and the output power gonna be changed. Same here, like current density, and we also compare like few different models just to see like the difference between the one that we tried and the other people tried. But you see that is quite close, although there are some differences. Now here, I'll finish this one, but only one more like an application. So here you can see that we have got 6 different model, and for all like the first one, like the full model that includes the thermodynamics that we mentioned, it's a highly nonlinear logarithmic dependence VSLI. And then for next one, we did consider some constant because here the problem is that the data availability. As I say that it's not easy to get all the data that you need to model that very detailed. And then we have got third, fourth, fifth and sixth model. So, this is the first one. How that other model looks like, I have given here like the third model, fourth model, fifth model and sixth model. Here you can see that. So, normally like people try like in the fourth level one. So, here you just have like one series and one parallel combination of resistance and capacitance. So, what I am trying to say that even if you consider all the dynamics, if you sometimes neglect some dynamics, if you and just to doing that, although you are going to be talking about the control system later, but again for doing that simulation, we did consider like the overall fuel cell control here, where you can see that because it's grid connected from PLL, we measured like the angle and then we use that one for active power control. Then we from voltage we have got reactive power control, and then current control as well, and how this control here I have shown like, although we are going to be talking all of them later, but what I am saying that using all the control, and initially we just try like very simple model that like a single machine to infinite bus, and then we tried like what's the difference like if you have like a simple model only single machine to infinite bus. And here you can see that when you think like the voltage and current, you can see that some of the cases you have got very high voltages, but in some cases like when you consider all the losses. So, if you consider the first one, it did consider all the losses, then your voltage is going to be lower. But the other cases when we do not consider the losses, you might get the voltage higher. But what I am trying to say that when you have got the current, although the amount is not significant, but whichever has got the lower voltage, you will get the higher current. But what I am trying to say at the end, if you measure the power, there is not that significant difference between all the models that I mentioned. So, if you are not that much interested for temperature variation, pressure variation, other things, then what I am trying to say that if you are just more like the power level interested, then if you just use the simple model, it's actually it's more than enough, and it is going to give you almost accurate behavior for all the things here. We tried voltage, power, frequency, and we haven't found any like significant difference of the response that we get from there. So, maybe I will stop here because we want to have a tutorial. The application I already mentioned, and also you can read the slide as well. So, with that I'll stop here, and then now we will try to connect for the tutorial, but at the same time I am here. If you have got any question, you can talk later, but you can try to connect now.
Thank you, Professor. So, as we will start the tutorial, but we can take questions up to 5 minutes.
At the same time he is like and I'm happy to take any question you might have.
So,
for transient analysis, which type of modeling do you prefer? Yes.
Well, again, even like if you consider that like the fourth level I mentioned, only for the power transient, like voltage and power, that is actually more than enough. We did number of, even like the control also was fine for voltage, but if you are more interested that I'm going to be seeing like how the pressure, temperature and other things changes, and that's I want to include it in the transient. then probably you need that model. But only for electrical output power, it is actually more than enough, even for transient analysis as well.
Eigenvalue analysis if we have to go for.
The eigenvalue again, I mean, because eigenvalue analysis, what we consider for eigenvalue, we consider a very small step change, right? So that's almost like many of the parameter is almost like constant. So that's simple, the parallel resistor capacitor with the series resistor is more than enough to do eigenvalue analysis.
Okay. So the equivalent model can be a better option, sir?
Sorry?
Equivalent model, the last one what you said, equivalent circuit model can be a better option?
Yes, that would be like a more than enough.
Option.
Yes.
Thank you, sir.
Because it's comparatively simple. Because when what happened, like if you want to do some eigenvalue analysis, and then you have got the modes, right? And then from modes you find whether it's stable or unstable, and then for that, if it is unstable, if you want to design the control by doing the participation analysis, that which factor is contributing, then when you have got so many parameters, sometimes it's not easy, to find out. So yeah, so in that cases, yeah. So what do you say lastly? Yeah, that's right. Yeah.
Sir, can we use the semi-empirical model for the MPPT control tech?
For MPPT control, again, the operating condition does not change significantly,
Okay.
then probably you can use that one. But if you see like that, very the variation is very large, then probably it's better to go for other model. But if you have a change, there is a change, but it's not that significant, then probably it's more than enough to do empirical model for MPPT.
Because sir, whatever the polarization curve we obtain in the MATLAB, right, in a semi-empirical model curve, so it will be exactly same. We can correlate with this.
That's right, because even if same empirical, but you are actually comparing with the the ideal condition one, right? And you play with how much how much error you can reduce by changing those parameters. So in that case, yeah, you can do that. Yeah.
Thank you, sir.
Yeah.
So thank you, and I'll share the slides of day one after the course, so you can go through the
So
slides.
this one online, right? So is that other student join? Can you I think he's going to join.
I request everyone to just open your MATLAB, and we'll have some online demo you will see. Basically the hands-on is basically whatever the theory you understood about the MATLAB, modeling of fuel cell. So those we are going to model using MATLAB environment.
So is it which one? He said that he could not join. He joined the other one probably. He says.
No, you have to. No, not this one. I sent the other one. No?
Is it the one that you sent?
No.
So that's why you need to join the one that you sent.
Sending you in WhatsApp now.
No, I think you already sent it. You just open that one.
Okay. This one, no?
Open now this one.
Here I have.
Yeah.
Hi, John. Can you ask?
Okay. Allah.
Can you share the screen?
Ah, yeah. Biplab, can you hear us?
Now?
Okay, just wait. Can you talk again?
Hello?
Yeah, it's good now. So, can you share your screen, please?
Yeah. Yeah, now?
Yes, I think all good. I mean, have you shared the screen? Just share the screen. We cannot see your screen yet.
Yep, got it.
So while he is doing, actually, Dr. Biplab, he recently finished PhD, and then he is also working like as a postdoc with me. So he did his PhD mainly on fuel cell as well as electrolyzer, and he used different model for doing dynamic analysis and also control design. So yes, Biplab, you share your screen, then you can start.
Now it's now?
We can see your desktop. You
Okay,
open that
yeah.
one, then share again.
Now I think it's work.
Yes. So we can see your paper. Yeah, and also all the MATLAB model, I mean, we can see that as well. Anyway.
Yep. So, sir, what should I have to present?
You can explain the model and then you can show some examples. That's all.
So you have presented from your side the theory.
Theory, I mean, the mathematics I did, but again, I mean, if you want, you can just tell them like, briefly, and then how you develop the model, which model you are showing. Yeah, so make some initial explanation.
Yeah. Hi everyone, am I audible now? Can
Yes.
you hear me?
Yes.
Yep. Thank you. So, if you've gone through some literature review on this topic, especially dynamic electrical equivalent modeling of proton exchange membrane fuel cell, this is the most demanded fuel cell. As you know, I think there are several types of fuel cell like alkaline fuel cell, proton exchange membrane fuel cell, and solid oxide fuel cell. But if we are focusing on renewable based power systems, then PEM, that means proton exchange membrane, is the best candidate because it can adjust its output current profile very quickly as compared to other candidates like alkaline and solid oxide. So that is why PEM, proton exchange membrane, is very suitable for especially for renewables, because for renewable based power generation systems, as we know, solar and wind, most of the most of the times they are changing in nature because of their dependency on climatic change. So that is why we are focusing today's my demonstrations focus more on proton exchange membrane fuel cell. So as we gone through some literature review, we see there are a lot of models available in the literature. Some are thermal models, some are chemical models, some are thermochemical model. So as a electrical engineering perspectives, we basically need electrical equivalent modeling, as we have resistor, capacitor, inductor. In same cases, we need a model circuit for electrical equivalent circuit for proton exchange membrane fuel cells. So this topic actually covers this. I think Professor Jahangir already describes its different kinds and different mathematical equations used to model for this electrical equivalent model. So I am just going through very quickly to start the main part of this sections. That means the equations, chemical equations used to related to the fuel cell is given here. Here we can see. So here there are entropy. This is the part of entropy, and this is the Gibbs free equations in terms of mole. So we can, from these equations, we can write Gibbs free equations in this way. In equation 2 you see. Then because fuel cell is a electrochemical devices, it contains anode and cathode. These are commonly said electroplates. So the movement of electron from anode to cathode, it requires some energy. Energy to energize the electron through the outside, through the conductor of the outside, that means through the other circuits. So this voltage can be defined by these equations. Here we can see the reversible voltage. The reversible voltage highly dependent on the pressures of hydrogens, pressures of oxygens, and the pressures of water. So we can rewrite these first equations in terms of entropy and the energy release required for the chemical reactions. In the second, in the below one, here we can see. And then there are some others voltage drops in the fuel cells. These are called activation over potential voltage drop, ohmic voltage drop, and concentrate voltage drop, or mass transport over potential drops. So the cell voltage across the fuel cell can be defined by these equations. If there are a lot of cells connected in either series or parallel, then this voltage of this combined system can be represented by this one. So now we are going towards activations over potentials. So as I already said, a fraction of the supplied voltage is dropped by the process of moving electrons between the electrodes, which is referred to activations over potentials. Here in these equations we can see activations over potentials basically split into two sections. One is for anodic activations over potential, another one is cathodic. So here we can see these two parts, anodic and cathodic here. So in broadly we can write these equations this way. Here we can see this way. If we combine this both anodic and cathodic, then we can generalizedly can write this one. So here is that one. So if we reverse the relationship, it is the relationship between activations over potential to the current passing from the from the fuel cell to the external circuits. So we can just reverse the relationship like this way. Here two new parameter, here we can see this is alpha A and alpha C. This is the standard current coefficients for anode, and this is the cathode. So these equations actually we need for modeling. Later we can see. Then the next one is concentration over potential, or we can say mass transportations over potentials. It is basically the results due to the fluctuations in concentrations of the reactants. So here the reactants are, one is hydrogen and another one is oxygens. So because of the fluctuations of hydrogen's pressure, temperatures, or any other dependent parameters, this overpotential has been resulted, and it's basically happened in high current density region, not low or moderate current densities. That is why most of the literature there ignore this term until 3 ampere per centimeter square. So this part can be defined here, the same as like activations over potentials. Concentrations over potentials can be defined by two sections. One is anodic and another one is cathodic. So here it is highly dependent on the reactants concentrations, as I said. So this is the nominal concentrations of one reactants, that means happened in anode, this is oxygens, and this is happened in cathode. So this is for hydrogen concentrations. This is the ratio between the measured concentrations and the nominal concentrations for the fuel cell. Similarly, combinedly, we can write these two sections in a one equations this way. So here the concentrations of oxygens and hydrogens can be written in broad sense here. So here we can see actually the concentrations of hydrogens or oxygens both are dependent on the current going through the external circuit from the fuel cells. So if we relate these two equations, we can say concentrations over potentials depends on the current moving towards the external circuit from the electrolyzer. So if this current density until this until this range, that means 3 ampere per centimeter square, then we can use these equations, and after that we can ignore this value. So here we can combinedly in short form we can write these equations for the concentrations over potentials. So the most important things for electrical circuit designing, this is the ohmic over potentials. So this is the ohmic over potentials that can be caused due to the resistance of the membrane placed between anode and cathode and the resistance of the contact. So this is the two main parameters to result this ohmic over potential. So here we can see in equations. So this is the very basic law, Ohm's law. So this is voltage equal IR. So this is the total ohmic voltage drop for across a single cell. So we can write this total resistance quantity into two parts. One is membranic resistive drop, another one is contact resistive drop. So membrane resistive drop is as we know, the name of this fuel cell is proton PEM, that means proton exchange membrane. So we basically put any type of proton exchange membrane in between anode and cathode. So this highly depends on the conductivity of this membrane. So here we can see it is basically depend on the membrane type. It is not fixed. So this is the dielectric constant of this membrane. So this conductivity basically based on the membrane, what type of membrane we use for design that. So and contact resistance is two types. One is the anodic contact. So here we can see the contact resistance. So it happens for both anode and cathode. This is the equivalent resistance circuits for the contact resistance. So it has some others parameter here we can see. So we don't need this detail for electrical equivalent modelings. So now how we can calculate the efficiency of a fuel cell? So for calculating the efficiency of a fuel cell, we first need to know for supplying a required amount of current, what would be the supply of hydrogen in the input side of the fuel cell. So it is that equations, that means this is the this is mole per this is the volume of the hydrogen that need for supplying a specific load. So this is the volume per mole. So this is the very basic equations taken from the chemistry. So here R is the universal gas constant, T is the ambient temperature, as you know. So from here we can just reduce we can just represent these equations in terms of time, that means milliliter per minute. So here we can see we can use these equations, then we can rewrite these equations in terms of this parameter, the parameter we have here. So just replace this one. So then we have these equations. So here also we can see the required number of fuel, it is called flow rate. Simply we can say this left hand parameter, left hand variable, simply we can say flow rate. So flow rate depends on the current. Other parts all are constant here except the current. So if we need more current, definitely we need to provide more flow rate in the input side. If we need, so if the current required is fluctuating in nature, then definitely based on this we need to readjust this flow rate. So here the another So this is the power supplied by the fuel cell. Here we can see it is based on the flow rate. So finally we can get the final equations. This is that one. That means the current supplying by the fuel cell and multiplied by reversible voltage. So this is the power. So then efficiency we can get, it is the ratio between nominal case and measured case. So finally we can find these equations. So from these equations, if we incorporate all the things, all three types of voltage drop as I mentioned here, all types of voltage drop, reversible voltage, activations over voltage, ohmic voltage and concentrations over voltage. So then we have a diagram figure like this way. Here we can see this is the mathematical model based electrical equivalent circuit of the proton exchange membrane electrolyzer. So here we can see, so this ohmic part actually represents the ohmic potential drops, these ones. So and here we can see there is a current dependent two parameters. One is for activation voltage over voltage and another one is for concentration voltage drop here. So another thing later we can see, when we can see the VI characteristics of this fuel cell, actually when we have a sudden change in the external current profile, voltage change doesn't change instantly. It needs some times to follow the external current profile change, because there is a time requirement to pass electron from one electrode to another electrode that cannot be reflected in the conductor, outside conductor. That means the conductor required to complete the circuit. This delay actually we can represent it by a first order time delay. So here we can see the transfer functions. Actually this voltage, this quick change current reflections take some times. This can be defined by this first order transfer functions. This is tau d. So tau equal the equivalent time required to pass electron from one electrode to another electrode through the membrane. So if we see the PI and VI characteristics curve of a proton exchange membrane fuel cell, here we can see very, after zero you see there is one range, one vertical range. This is actually the low, very low current density regions, and this voltage actually, this regions actually represents activations voltage drop, because this is the very minimum voltage you have to supply between electrodes to energize electron to transfer one electrode to another electrode, let us say anode to cathode. So until supplying this voltage, it cannot be start supplying current to the external circuit or power to the external circuit. So that is why this voltage reflects in the very low current density. So you see this is also non-linear. The nature of this curve is non-linear. Here we can see if we make little bit zoom, you see this is non-linear curve. Because if we see the equations, final equations here activation voltage drop, you see it is not a linear relation, it is a non-linear relations. So that is why this curve also shows non-linearity here. And after that you see until this vertical range, here we see another vertical, this region is a linear region, because this region occurs due to the ohmic voltage drop, and according to the Ohm's law, it is a ohmic voltage drop. Definitely it depends only V equal IR, only the resistive elements. So it is a linear region, you see. And from this curve we can say there is another regions after this vertical line. There is another regions. This is a high current density regions, and this regions there is another voltage drop. This is mass transport over potential drops or concentration drops. Here we can see. So this is also nonlinear because of their mathematical nature. From this mathematical nature we can see. So this line, actually this curve is VI characteristics curve, and another curve if we draw here, it is based on current versus power curve. So this is called PI characteristics curve. So it's look like that. If we multiply each points, P equal VI. So if we multiply each points current into current and voltage, then we can easily get this power characteristics curve. The intersections between VI and PI characteristics curve, here we can see this is the intersections point. Actually this point defines the optimal operating point of this fuel cell. We always try to operate this fuel cell at the intersections point, or it is called nominal operating point. And this one, the red, you see the red dot, this is the maximum power operating point. That means at this point we have very extreme limit of the ohmic region. You see, this is, it actually happens the extreme limit of the ohmic voltage drop regions. And after that we have nonlinear, so it suddenly reduce the power. You see here, because of the nonlinear characteristics happens due to the concentrations voltage drop. So here you see in this equivalent circuit diagram we use a first order transfer functions. So this is actually explained here. From the first order circuit we have this one. This is the basic equations of a first order RC circuit. If there is RC circuit, so this one, so this is the first order time delay. So as we know, this is time constant in another term we can say. So time constant equal RC. So R actually is the equivalent resistance of ohmic and anodic and cathodic voltage drop. This is the equivalent resistance, and CD is the equivalent delay to transfer electron from one electrode to another electrode. So this is actually the basics, mathematics and the modelings of a proton exchange membrane electrolyzer, fuel cell.
Maybe now we go for like MATLAB. Can you please?
Yeah. Now I'm going to a very simple circuits. So I previously modified a circuits for you. So this is the fuel.
Yeah, Biplab, just a minute. So have you given that circuit to everyone?
This one?
Okay, I mean, if they want to build it, it might be. Yeah, I mean, Biplab, you just you start the existing one from MATLAB.
Yes, sir. I actually prepare 3 tasks for the attendee. So after just describing this model inside, so I will give them this task. Is it okay?
Maybe you just open the existing model from there.
Yeah.
So, and then if they want to do it, how they gonna find the model? You can show them, because
so we can find, yep. So if this is the Simulink interface of MATLAB. So if you double click right on your mouse, double click the cursor, so then there is a new pop-up, search block will come. You just write here fuel cell. So we need to use this one because we are going to model electrical circuits. So that is why we need electrical specialized power systems. So just click this one. So you see the similar block comes
so
here.
I mean, just wait there, just to see like, has everyone got this block, MATLAB? Anyone have problem? Okay, no, then you keep continue. Yes, like after like this model, maybe just explain little bit inside what is there and then go from there.
Yeah, if you double click the block, this fuel cell stack block, double click, right cursor. So here we can see actually you can use your own developed model, or you can use built-in model provided by MATLAB. So preset model. So here we can see there are a lot of, so if you choose this one, you can then provide the details of your own developed model in the remaining, below blocks, below field. If you, there are other some built-in stacks. So you see this is proton exchange membrane fuel cell. This is 1.26 kilowatt and it can provide 24 volt DC at the output terminal for nominal operations. Another one is, this is also PM, it is 6 kilowatt 45 VDC. So in such way you can either use built-in fuel cell or you can use your own defined fuel cell. For example, here for this one I am using 6 kilowatt 45 VDC fuel cell stack and this is PM. So after that, so this parameter sections you can define here. So you see voltage at open circuits and 1 ampere. So you can define this voltage at 0 ampere and 1 ampere. If you click here, the VI characteristics curve here, so you see the VI characteristics curve, the upper one, and the lower one is the power characteristics curve. So if you combine these two ones, so this is the intersections point. So it is called the nominal operating point. So what would be the value at 1 ampere you can define. What would be the, in such way you can define other remaining network parameters. So stack parameters like this way. So what would be the nominal current, what would be the nominal voltage you can define here. So we can see here the nominal current is 133 and nominal voltage is 3.45. If you click the VI characteristics curve, we can see the same value here. So you see 133 is the ampere and 3.45 is the voltage for this. Sorry, 133.3 is the current and 45 is the voltage. So in such way the nominal power this much 6 kilowatt. In such way you can define the characteristics curve of your own defined. So if you choose any one, built, you see most of these things are hidden now, inactive. You can't insert this value because this is built in. So after then another field, this is called signal variations. So what type of fuel consumptions you have to input in your fuel cell stack, you can provide it by using external input probe. Like if you click here one, so there is an input probe you can define here the fuel consumption percentage. Like
so what is here, like, I mean, there are some internal, but if someone wants to give their own input, they can do it, right?
Yeah. So if you want to provide a specific value from your design perspective, you can put. Otherwise, if you doesn't select any input probe, then all things actually the built-in functions thinks all the input are sufficient. They provide current and voltage based on these things. They are thinking that all things are provided sufficient. There is no deficiency. And if you want to make it more realistic, like there might have some deficiency, there is some surplus this value, then you can provide this specific value. So after then, this is the fuel cell dynamics. So actually if you want to fuel cell dynamics, actually this is the time. The time, as I said, first order time delay, you can define this time from here. So these are the parameters input things. So just I'm going through a little bit quicker with this help. So this is that circuit, but the available MATLAB built-in circuit, they are ignoring concentrations over voltage. Here we can see this is the equivalent of ohmic voltage, this resistance part, and there is a current dependent one parameter only, you see. So this is the equations for activation voltage drop only. There is no another parallel connections in this presentations, you see there are two sections parallelly connected. So one is for activation voltage drop, another one is for concentration voltage drop. But MATLAB built in one, there is no concentration voltage drop. It is designed for low current density applications. So the same things here we can see, this is the activation voltage drop region, this is the ohmic regions, and this is the concentration voltage drop regions. The equations I showed, they are explaining this all equations here. And here we can see if we want to input this parameter, we can easily input this parameter by selecting from the signal sections. So this is the equations for utilization factor. For example, for battery, we know the term SOC, state of charge. Basically, we are going to use battery for a manufacturer specified range, like 10% SOC to 90% SOC, or 50% SOC to 70% SOC. Same way, we have to define here fuel utilization factor. One is for hydrogen, another one is for oxygen. If you want, then, for example, the wise practice for fuel cell operations, hydrogen utilization factor keeps between 80% to 90%. More specifically, it is 85%. So in such way, you can define this value from using these equations. So these are the equations how you can calculate pressures of each reactants by using the compositions of fuels. So this is the equations here we can already describe. Another important thing we need, this is at the end we can see here, this is the fuel flow rate. Fuel flow rate. So actually, if we need a specific amount of current need to be supplied across a load, so based on this requirement, we need to supply the required flow rate either for hydrogen or air, that means oxygens. So we can define these things using these equations. So using these equations, so these are the basics about the built-in fuel cell stack provided by the MATLAB. So these are the basics.
There's just one like 10 minutes break. So meantime you can have a tea or something like that, and then you can give like showing how to do that simulation. Okay.
Okay. Yeah.
So
thank you.
yeah,
Okay.
so that's just like 10 minutes. So you can start after 10 minutes.
So some tea arrangement is there in the registration room. So we'll have a 10 minutes break. Then we'll model it.
Yeah. Please don't take.
Yeah.
10
Please
minutes because we're gonna
be on
finish,
time.
By
Yeah.
okay.
So Jahangir sir,
Yes.
আপনি কি India? You are in India?
Yes. Just go like do under mask, like show like different component, and then I don't know, whatever simulation you want to show, you can show that now.
Okay. So then they don't do any simulations by their own self. I have to demonstrate.
Maybe some of them have done. I'm not sure. How many of you have done any simulation?
I'm preparing here 3 tasks.
I think few of them done, but please show them first, like considering that they don't know anything, how they should start in MATLAB.
Yeah. Yeah. Okay, so
please try to go with him, and any issue, let us know.
yeah, so here first at all we are going to develop task 1. Here we see this is a very simple circuit. Build a simple circuit where a simple load is connected with PMFC stack and observe the voltage, current and power characteristics. So for doing that, use 45 volt 6 kilowatt built-in fuel cell stack, a series RLC branch for loads and a scope for results observations. So we are trying to do the first one. It is for the very beginner. So if we first click MATLAB, so this interface will open. So this is the programming interface. From here we can see. So it is also vary from version to version. So this is 2023 A version. So if we need to go first Simulink here. So this is the Simulink. So from this Simulink we need to take a blank model. So this is the blank model. So on this interface, if you clicking double in your right cursor of your mouse, then this kind of pop-up will show. Just right here, fuel cell, as I say, fuel cell stack. So we can take a fuel cell stack like this. So after clicking double on this block, so we are selecting like simplified model, and this is 6 kilowatt, for example. This one we are going to take. So click it OK. So from here we can connect any load across the positive and negative. So again the same things. If we need any components anytime, just double click your right cursor and then right here like series RLC branch, for example we are taking this one, series RLC branch. So if you click here, then we can do some rotations like orientations or format. So here we can see rotations. So if we double click, if we want to change the parameters of this, just double click. Similarly like fuel cell, double click. So if we want to take only resistance, we can take. So it's, and this value, like if we want to see, for example here, so the current is this much and voltage is this one. So according to Ohm's law, we can put any value, but we are putting like this, 45 over 1 on this mass. For example, this is the resistance value. So click it. Then if we go close to the terminal like positive, negative, then it will automatic comes where you just drag and connect to your other points. You see, just drag it to the other terminal. So it is the very simple circuits. So now we have to measure the voltage, currents and power of this one. So how can we do? Just double click here, same way, voltage measurements. We just take voltage measurements. It is actually voltmeter. Physically, the things we do in our laboratory lab, this is voltmeter. So we just remove one and make it plus here. Oh, sorry. So we have to connect voltmeter in parallel because we are measuring voltage. So plus here, plus here, and it shows us the signal value, the what would be the voltage across these two terminal. So we can choose this one. Then similarly we need to measure current. So we can write the same things, current measurement. So plus this is minus. So this one give us the current passing through this branch. So now we have to see the value in oscilloscope. So we can write here is scope. So then it is like oscilloscope, the things we are doing in the lab. So double click here, so we can change its property, many things. The way we are want to observe the results, we can do. For example, we are taking here two scope, so layout should be like this way, vertically. So you see there are two scope. If we want to see current in the bottom scope, just connect it, and voltage to the up scope we can see. So here if we click now run, then you see there is a error. So that means this circuit is not complete because we are taking fuel cell from, if we again go like fuel cell. So here the library name is specialized power system or sources. So if we use any components from this library, specialized power systems or sources, we need another component. This is called power GUI. Power GUI, here we can see. So we need this one. So it has 3 mode of operations. So these are the detailed things. So here we can see 4 mode of operations: continuous, discrete, phasor and discrete phasor. So we keep for this one continuous. Now if we are going to build this model, so this model is now, there is no error. If we see, so you see it's almost 45 volts in the voltage, measured voltage, this one, and the current is 133 like this. If we want to make it bigger, yeah, it's the same value. That means the value we are inputting here 133.3. So this way we can use this fuel cell as one of the DC voltage source. This is just simply one kind of DC voltage source, but it operates, it needs hydrogen as a fuel. That means it is a kind of machine which takes a chemical energy, that means hydrogen as a input, and provide electrical energy as a output. So this is a very simple circuits. So in this way we can, step by step can develop more complex circuits. So we can move to the next. So until now, anyone has any question?
Any question or problem? Or all good? So one of them asking like you have considered continuous, right?
Yeah.
But there is like, so when you have got like phasor measurement, so that means like RMS,
Correct.
right?
Yeah,
it's
yeah.
like only
There is-
electromechanical. But if you consider like continuous and discrete, you are also considering some other dynamics as well. Is that everything, or you want to add anything, Biplab?
Sir, for continuous and discrete, actually, if you want to incorporate in your design any power electronics, that means is there any non-linear switching element?
Yes. So when you have got like
So-
nonlinear switch, power electronics, then you have to go for discrete model, right?
Yeah, discrete. And if you have only mathematical model, that means you don't have any components like this IGBT, then any diode, then any transistor, then we don't need, then you can go only phasor mode. For phasor mode is little bit quicker. Actually, this provides you RMS analysis.
Yeah.
So if, for example, if we change it from continuous to discrete, for this case actually, and this is the sample times, that means it's based on the iterations as solutions. So from one time step to another time step, it takes your defined value. For example, if we are taking 50 milliseconds time step, so the total simulation time you see, this much 10 seconds. So how many iterations it will have now? So it just this much divided by this value, like it is a specific iterations. To cover this time, it actually solve this model for a specific iterations, not continuous.
Yeah.
So
Yeah.
one more question. Now say rather than using this fuel stack from the Simulink library, if we build this fuel stack model
Yes.
using equations, then what we need to
Yeah,
use
yeah.
there?
Yeah, you can do it using your own.
So there is
Actually-
like a user defined function, right?
Yeah, yeah. So for that, I can show you. So for example, if you have, you can do these things two way. For example, if you double click here, then you can just choose your user defined. So you need then manufacturer value, like what would be the open circuit voltage. So you need this manufacturer value to complete your user defined. If you have any handwriting, hand calculating value, you can use this one. Or if you have any manufacturing value, that means you are collecting from literature, or you have
So I think
you have
Biplab,
bought from your.
Biplab, I mean, her question is like, I understand that if you use like user defined, but still you don't need to write equation. They're gonna use the inbuilt equation by using the input parameter that you're gonna make as an input.
Yep.
But other way also, I mean, what she is asking that she's not gonna use this model. So
Yeah.
if she wants to develop, so I think two way, I think you can done like using M-file like one way that you just model that equation that he discussed like in detail in that paper. So it's a simple equation. You write MATLAB code using defining some function or for loop. The one way you can do it. Other way also you can do it using Simulink. There is like a user defined function. Yeah.
We should use it as phasor or as continuous?
You mean in
Which
Simulink or
one?
M-file?
M-file.
M-file,
M-file, M-file and
M-file you
Simulink.
don't need. M-file
No
you
sir,
don't need.
M-file and Simulink both are linked.
Yeah, you can link both as well, but
That-
you can also do also separately. Like only M file also is possible.
Okay, okay.
Only M file. You are not using any block. You are just using the MATLAB coding.
Yeah, but when I use both, then what
You can
has
use
to
both.
we can use? Then that time, what should be that power GUI? What we should use? Whether it is continuous or phasor?
Power
Then-
GUI actually you need if you want any component from specialized power electronics sources or
Yes.
components library. Any components from this library, if you are going to use, then you need Power GUI only.
But if you just use like normal user defined block, you don't need that, because in that case,
Yeah, you
you
don't
are
need.
not using their existing component.
Because I am using MATLAB developed fuel cell stack and series RLC branch. These all things you can find only within specialized power sources or components library. So if any components, even a tiny components like voltage measurement, current measurement, if you use any simple components, then you definitely need to use Power GUI.
Yeah, so we can't see your like skin now. So
Yep. It's not showing.
okay, so you can show like what is under the mask, and then you can just do the simulation showing the result. Can you just go a little bit under the mask?
Under the
mask, like showing different subsystems.
yep. So if you want to see the details how this block has been created, just go mask, then
So we
look
can't- we
under
can-
mask.
Maybe you need to share again. We cannot see. Maybe unshare everything and then share.
Okay. Now?
Yes, now we can see. Yes.
So, for example, if this is the block, how this block can be built. So you just right click, then go mask, look under mask. So if you go, it is basically based on the mathematics. So the things, all input are given here. You see the air pressures, all things. So if we go, this is the model. So if we use continuous detail, then it's automatic, select this block. There are lot of blocks they have created. It's based on the Power GUI option, selection option. So if we are using continuous detail, then it should, focus only this block. If we are choosing continuous simplified, then it should only use this block. So like this way, discrete detail, this way, and discrete simplified. There are, for example, we are solving this model using discrete. So discrete, if we click here, and this is detail. So based on our, input value here, so they are using this one, discrete detail, that means this one. So if you click this one, so you see these all are the input. That means, if we go back these equations, there are a lot of input variable, and based on this output variable, so this is actually the voltage, utilization factor calculator, partial pressures calculator. So all things are given inside this.
So at the end,
So-
you just need to know the equation and how you are solving. That depends on your preference, either using the block or using simple coding and so on. Yes, continue.
So just a moment, I have the things students are asking. I have the same things. Just one
Okay.
second, I have
Okay.
to open it. Yep. Here we can see, can you see this model?
Yes.
Here you see, this is the model, that means this is the electrolyzer, it is connected. This is not fuel cell, but the principle is very similar. When input is hydrogen, then it is fuel cell, then when input is electricity and output is hydrogen, then it is electrolyzer. So you think it is a kind of fuel cell. So here we can see, if we go inside this, so the professor said you, this is the MATLAB functions block. Here we can see, we defined all things. This is the ohmic drops, this is the length of the membrane thickness. So these all are given. This is the area of the activation membrane. So this is the number of series connected cell. This is the number of parallel connected cell to make the stack. This is the ideal gas constant. So this way we are inputting here all values. So from there, this is the reference temperature and pressures. All things are operating parameters. It is my developed model. So here we can see how we can calculate internal resistance.
Can you see like that? You are just writing the equation. In MATLAB, you know, solving is very
MATLAB code.
very simple. You just giving the input and whatever equation you are just writing.
Okay, here for example, this is the
You can do it by yourself.
Gibbs-free
You don't have to use
equations.
their model. It's very simple to do it by this way as well. Yes, yeah, continue.
So here we can see this is the Gibbs-free equations. The same equations I represent you in my presentations. But it definitely needs time. Actually, you can't do it one day or 2 days. So it definitely needs time. For example, if we are picking from any equations, yep, so this is, you see this part, delta Z over ZF. So this reversible equations is developed here. Delta Z reversible 2F. Z means the number of electron. For oxygen, for hydrogen, there is H2. The compound is H2. So number of hydrogen is 2. So this is that value. So this is the equations for over voltage potentials drop. Here we can see this is the equations for over voltage potential drop. If we go these equations again, so these are the simple things actually.
Yeah, I mean,
So this is that equations.
it will take some time, but it's not that difficult to do it.
Yeah, just I have write these equations here. So in Sahoo, so this is the hydrogen productions, that means milliliter per minute. That things I already showed you. So this is the power based on the hydrogen supplied. This is the power. So in Sahoo you can easily develop. So if I am going back again, you see this is the, that means if we want to develop based on this mathematics, so this is that functions. There is, you can easily then connect other components, like this is a boost converter. Sorry, this is a boost converter. You see, this is a boost converter connecting between the source and load. For example, in this our current model here, where is that model? Here, so here we can see there is no, so this is the load and this is the source. Here we are not using any converter like DC-DC buck, boost, any kind of power electronic interface we are not using here. So that is why, but if we want, you can use, it's like this way. Here it is a boost converter. So this way, and this is the another model. So here we can see how we can, this is the hydrogen tank model. So I'm just showing you the same way using mathematical functions. That means mathematical, scripting, we are developing the tank pressures. So any model, you can either use block or you can either use script scripting inside this MATLAB functions block. This is the MATLAB functions block.
So that's the one I was talking about, that you can use any MATLAB function to write down your own equation coding here. So yeah.
And it's definitely reduce the number of block as well. You see many things we can do inside a single block.
Yeah.
So any questions until now?
No, I think all good. I mean, whatever you want to show now. So just show some result, how they can produce some result and show the performance.
Okay, for this one, the same circuits actually, here we see there is a measurement terminal. So if we want to see the measured parameters, different parameters of this fuel cell stack, like what is the utilizations. So if you click here, at the bottom side, there is a measure. No, it's built in. So it means there is a, so if you click here, these things you can actually, by default, you can observe this kind of, results, this kind of parameters. So voltage, current, stack efficiency. So this way you can observe this one. So I am now using this, using this bus selector, I am only observing these three parameters: utilizations, stack consumptions, that means liter per minute, and stack efficiency. So if we run this model, yeah. So here we see utilizations. These are two type of utilizations: oxygen utilizations and hydrogen utilizations. So if you put some legend, then we can have. So oxygen utilizations is the yellow color. That means this is 60% and 100% hydrogen utilizations. So the fuel consumptions liter per minute, that means for providing this output, that means if we want to increase load here, so based on this the current also increases. So if the current increases, then the supply of both air flow rate and fuel flow rate both need to be increased. So this kind of things actually, this way you can see the results. And the stack efficiency is how much? Here we can see. So the stack, so stack is operated in between 66% to 68% efficiency. So this one, so before we took here voltage, for example, if we have to remove here, so this is double click, voltage, measurement block, the same things we have just placed here. So this line actually, this line here we see, this is the first channel. In this oscilloscope we have 3 channels. The first channel, there are 2 input, this one and this one. So this one measuring our, you see from here, so the same line, this one measuring our voltage, the lower one, and this one measuring our fuel cell stack voltage. So here we can see this is the stack voltage and this is the voltage across the load. So if we go the first channel 1 only, here we can see this is the first channel 1. Channel 1, so if we put here legend, so you see the voltage between the voltage across the load and the voltage of stack same, because it is 45 volts and this load is connected parallel with this terminal. So that is why the same voltage we can observe from here. So if we click here, then this one hide, this one highlighted, because the same value, that is why it's overlap one other. If there are different value, then we can see difference. For example, here if we connect another resistor in series, then there are two branches, RL, two resistive branch. So this voltage measurement, this voltmeter measures voltage only this one, but this one and the voltage across the fuel cell is the combinations of this one plus this one. So you can see now the difference. For example, you see now the voltage across this one, only this one is reduced, and this is since the branch resistance this one and this one equal, that is why the voltage reduced to half, 45 to half, I think. Here we see this is the almost half of this. So this way actually we can see the results. So similarly, like here we are inserting here this component, this is ammeter or current measurement. So we place it in series. So you see, so this one actually goes here. So this is the current supplying by this electrolyte fuel cell, and this one the current we are measuring from here. That means the second channel of this scope measured current. So here we can see this is the second. So both current, this is a series circuit. So this is why both parameter are same. You see, same. This one actually, the third channel here measured the power. So this is the total supply power by this fuel cell, and another one the power consumed only by this resistor using a product block. That means voltage multiplied by current give us DC power. So one is for power consumed by this electrolyzer, this load, DC load, and another one is supplied by the fuel cell. That means this one. So if we see the third channel, here we can see. So this is the total power supplied by the fuel cell, and this is the power consumed by the load, only the second load. So now this is the basics. So have a look on it, and can you do some little modifications of this circuit based on these questions, task 2. Yep, just see here.
So we have got like another 10 minutes. I don't know, I mean, if you want to try now, otherwise maybe you have to try later. So Biplav,
Yes, sir.
you just give like hints how to do it, and then you send me the task, I'll give it to them. But just give some hints how they can do it, and then you can finish it.
Yeah, so here we see the same things. Actually here, from here we are selecting this one, 6 kilowatt 45 volt DC. So based on this, the power supplied by this fuel cell, definitely equal to 6 kilowatt, and the voltage across this terminal, positive and negative terminal of this fuel cell, it should be 45 volts. But from here, if we see the voltage supplied by the stack, this is the yellow one, so this is more than 45 volts, you see. So my question is why? Because the nominal operating voltage of this fuel cell is 45 volt, but you see the voltage higher than the nominal voltage, 45. And also power, the maximum power supplied by this fuel cell is 1 kilowatt, not 6 kilowatt. So that is why if we go back again to this fuel cell model, for example, VI characteristics, so we can operate this fuel cell any region of this characteristics line, any region. But this one only our operating, nominal operating point. So here the voltage is 45 and current is 133.3. But if we see our results, so this is how much. So if we make it little bit zoom, so our fuel cell operate at like 57 volts. So if we go back again this plot, so 57 means like I think, so we can assume this point, so like this one 57, 56, 57. So for example this point, you see the current is how much, 20.25. so if you see again this, so you see our current like this one, total currents, so it is like this much, total current 17. So that means from this point we can see, so our fuel cell actually operate this point, not this point, because this is open loop. We are connecting load across the fuel cell as a open loop manner. There is no closed loop control. That is why, so at that point if you divide these two value, the resistance definitely is very less resistance. So according to the nature of from the relative resistivity law, we can know current has tendency to pass low resistive path. So if this fuel cell operate at this point, so why need to operate that point? No need. So easily they are selecting this point or any other random points at this point or this point. So it's not operate. So for operating this one, we need another device. This is control device that can help to operate this fuel cell at the nominal point, because if we have reference current that can bound the circuit to operate at that point. For example, if we develop a controller that can bound the circuit to operate the current at 133.3 ampere, if the current is this much, then definitely voltage come back to 45 volts. So that is why we need some reference value, we need to provide some measured value. So where we can insert this value, we can input it in any electronic power electronic device. That is why in my questions I put here, we can do it using a DC-DC converter, either it is boost or buck. From here we can put the reference current or voltage to operate the fuel cell stack. So in Sahoo we can operate fuel cell at its nominal operating point or any other operating points. Can you guys try it? If you can try first, if is it possible, otherwise I can show you. Just thinking, because I think you have massive knowledge how to develop DC-DC converter, buck, boost, or using separate IGBT or separate transistor, or using built-in. There is in MATLAB there are a lot different type of different type of built-in converter, using chopper, using 2 level, 3 level, different. So just try to think it.
Hello.
Hi.
Can you hear me?
Yes.
So they're going to do it later at home. She just explain what the other final task, and then you can finish in 2 minutes.
I have to finish within 2 minutes.
Yeah, so just explain what the other task. And they're
So
going to try
another thing
their
I-
home.
Yeah, so another thing, task 3. So as here we can show you here at the very first time, so we can use any user defined functions from here. We can input any input. So for example, in this design, I input fuel flow rate. So just, so here, so how we can use this type of user defined signal in our fuel cell stack. One example is that one, simple circuit through DC-DC converter to operate the using user defined signal, for example flow rate or oxygen rate or user defined utilization factor. So this is the another thing. So for that one I am explaining this one. So this is the last task. So you see this is the same circuit here. In between the fuel cell and load, I am inputting here one DC-DC converter. That means that this is the second one. So here we can see this is the DC-DC converter. So this is the measured voltage. So we input this measured voltage, for example 45 volts. So this is our reference voltage. For example, this is our reference voltage, for example 100. So this control, this is PI based control strategy. This controller actually try to adjust the measure voltage, whatever it is, make it equal to 100 voltage. So if we have known operating point voltage, then we can easily operate this stack at a specific voltage. So this is the second one. And third one, here we can see we are using here fuel flow rate. So for that we are taking input from here. We are taking input current, and then if we go inside this one, this block, there is a functions block. They are actually using a mathematical calculations. In this calculations only the current is the input and other all parameters are the constant. So if we go back, only input is current and other all are the constant. From where we get these equations, I showed you at the very beginning. Go to help, they are showing you the equations how we can. Yep, you see, yeah, these equations actually is start from 60,000 from here, 60,000. So if we go back here, so in this design, so you see it also start from 60,000 because it is based on the same equation. Just we have write here these equations. So then you can easily, in such way, you can easily input your user defined signal based on your current profile. That means if it is highly fluctuating in nature, then you can, based on that, you can develop these equations and readjust the fuel flow rate to ensure that your fuel cell stack operate your defined utilization factor, like 80%, 90%, whatever you want to operate this fuel cell. These things actually ensure you that your fuel cell operate at that particular value. So that's all, sir, from my side. Any questions?
So we'll have, do you
Biplav,
Yes.
thanks for your time. So you can just email me those tasks. I will give them, and they're going to try their home later because we don't have enough time to do it now. Again, many thanks for your time. So you can probably disconnect. But email me those things that you have done. I'll give them that MATLAB model and the things that you said, they're going to practice by themselves.
Okay, thank you so much.
Just email me everything, and then I'm going to give them. Okay? Thank you.
Yeah, I'm now after leaving. I will send you email. Yep. Thank you so much. Have a good night. Bye bye.
So thank you everyone. So here we came to an end of day 1. Hopefully you learned something, and both on theory as well as some modeling part. We'll continue tomorrow, and tomorrow we'll start at 10 a.m. in the same room. So kindly join on time. Thank you. Good night.
Again, I mean, as you mentioned in the morning, that this is just like giving you some starting point. I mean, what you can do.